So in the last video, I talked about being able to use the central limit theorem to find probabilities. Section 4 is going to be talking about creating or estimating the population proportion with confidence intervals. So like we have seen throughout this chapter, the population proportion is not always given to us, and in the case where it's not given to us, we can't do anything about it because it's unknown. And so in this section, we're going to be using confidence intervals to estimate the population proportion. And so if we're trying to estimate the population proportion with the confidence intervals, we're assuming that the population proportion is unknown. So what is a confidence interval or intervals? So the word intervals tells us that this is going to be a range of values. This range of values is going to be calculated based on our sample and is going to be very likely to contain our unknown parameter. So our confidence interval, as I've mentioned, is a range of values. So we're going to have a lower and an upper value. And this is going to be calculated based on our sample. The confidence interval will always include a confidence level. What is the difference between the two? The confidence interval is the range that we think our parameter is in. So the range of values that we think our parameter is in between. Whereas the confidence level is how sure or how confident we are of this. Some of the most common confidence levels are 90%, 95%, and 99%. The most common one that we use is 95%, because 95% is a good balance between being confident and being uncertain. So when we are 90% sure, our interval is going to be slightly smaller. When we are 95% sure, our interval or our range of values that our parameter could possibly be in becomes bigger. And when we are 99% sure, then our interval includes most of all of the values, with very, very minimal room for mistake. So let's look at what this means. So here I have my lower and upper bound. This should be a U. So the entire range from the lower to the upper bound is going to be 100% of the data values. When we are 90% confident, we're assuming that our parameter is going to fall within this red region right here. But when we're 95% confident, we have a larger bound. We're saying that our parameter can be contained in this second red region. But when we're 99% confident, we're saying that our parameter, our unknown parameter, will be contained somewhere in this whole region right here. But again, like I've mentioned, the higher your confidence level isn't always a good thing, because when your confidence level is so high, you give yourself very little room to make a mistake. So a 95% confidence level tells us that we are 95% sure or confident that the interval will capture our true population parameter, giving us a 5% uncertainty. Whereas a 99% confidence level, we're more confident and we're more sure, but that only gives us 1% to make a mistake or for uncertainty. And so sometimes when your confidence level is too high, that's going to lower the power of your study. Let's look at how the empirical rule applies to the confidence intervals. So I hope that you remember what the empirical rule is. The empirical rule tells us that 68% of the data are captured within 1 standard deviation, 95% is captured within 2, and then 99.7% is captured within 3. So in this case, if a distribution meets the CLC requirements and is approximately normal, then the empirical rule will also hold and be true. This is going to be very helpful for us because this is going to be assumed in our calculation when we're trying to calculate the confidence intervals. So again, I want to re-emphasize, if we are 95% confident, then by the empirical rule, we're 95% confident that the data is going to be within 2 standard deviations of the mean. How do we find the 95% confidence interval? So the formula for the 95% confidence interval is going to look like this. This is not the complete formula yet. I'm going to add one more thing to this formula to make it complete. So here, our confidence interval is going to be p hat plus or minus the z-score times the standard error estimated. So again, as I mentioned at the very beginning of this video, the confidence interval depends on the sample. So everything is constructed based on the sample proportion and the standard error estimated, never on the population proportion or the standard error. Z in this case right here corresponds to our confidence interval. So if the confidence interval is 95%, then Z is going to be 2, because we know that by the empirical rule, 95% of the data is within 2 standard deviations. I do want to mention that in your MyStatLab homework, they don't use 2, they use 1.96, which is actually the actual z-score associated with 95%. And so in the examples that I do, I use 2, but in your homework, and if you prefer to use 1.96, go ahead and do that. It's going to be good practice for your MyStatLab assignment. And then again, a reminder, the standard error estimated is this right here. Before we get into actually calculating some stuff, let's look at another term. This term is known as the margin of error. The margin of error just tells us how far our estimate is away from our population value. How do we find the margin of error? The margin of error has this formula right here. So margin of error, I'm going to call it ME, or I'm going to denote it as ME. So the margin of error is the z-score times the standard error estimated. And so if you, for a 95% confidence interval, the margin of error will have a z that's equal to 2. Because again, by the empirical rule, we know that 95% of the data is within 2 standard deviations. I want to make a quick note that the margin of error right here, z times SE estimated, this is actually a part of the 95% confidence interval equation. Because isn't this part right here just the margin of error? Z times SE estimated. So as long as you have calculated your confidence interval already, you already calculated your margin of error. So there's no need to be doing extra work if you've already calculated the confidence interval. Okay, so let's move on to our 5th example. So here we're going to take what we've just learned about confidence interval and actually apply it to this problem. So here we're told that about 200 million Americans attend college each year. We want to estimate the population proportion of students who borrow money annually. 500 American college students were randomly surveyed about college debt and found that 58% of them borrow money annually. So the task is to find and interpret the 95% confidence interval. So I'm going to quickly write what the interval formula is so that we have that in mind. So the 95% confidence interval is p hat plus and minus 2 times the standard error estimated. Again, remember that in your MyStatLab homework, they're going to make you use 1.96, so it might be a good habit to start doing it using 1.96 instead. So looking at this formula right here, there are 2 things that we need in order to calculate the confidence interval. First, we need p hat. And then we need the standard error estimated. So p-hat is going to depend on the sample. So out of the 500, how many of them borrow money annually? And nicely, this example provides it for us without us having to calculate it. So p-hat is 0.58 because from this example, or from the information provided, they tell us that 58% of them borrow money annually. The standard error, we will have to calculate that, but we have the fancy formula for that. So the standard error is p-hat times the quantity 1 minus p-hat all over n, and don't forget the square root. N, what is n? So n is the sample size. So how many people were sampled for the study? 500. So n is 500. So since we have p-hat and we have n, we can calculate the standard error, which is going to be 0.58. So after solving this out, your standard error should be 0.0219. So now we have everything we need in order to calculate the confidence interval. And so again, I'm going to write it down here. The 95% confidence interval is going to be p-hat plus and minus 2 times the standard error estimated, which is 0.5 plus or minus 2 times 0.0219. And if you actually find the product of it, you would get 0.0438. So when you get to the step right here we have a plus and minus sign, which means that we have to take 0.58 minus 0.0438, and then we also have to take 0.58 plus 0.0438. The confidence interval is a range of values, so we're going to be getting two numbers. And so to indicate that it's an interval, I'm going to be using the brackets with a comma in between the two numbers. So the first number is going to be the lower bound. The second number is going to be the upper bound. So the lower bound is going to depend on taking 0.58 and subtracting the margin of error. So again, remember that the margin of error is the z-squared, or the z times the standard error estimated, which in this case is 0.0438. So the lower bound is p-hat minus the margin of error. So if you solve that out, you should be getting a lower bound of 0.5562. The upper bound comes from taking 0.48 and adding 0.0438, or taking p-hat and adding the margin of error to it, which in this case is going to yield 0.6438. So here we have our confidence interval. Again, our confidence interval is a range of values, so you have a lower and an upper bound. So what does this mean specifically in this problem? Again, we want to find, or we want to estimate the population proportion of students who borrow money annually. And so to answer the question, the interpretation would be that we are 95% confident that the population proportion of all 200 million Americans who attend college each year will be between 0.5562 and 0.6438. So this confidence interval was constructed with the sample that we had and the available information. Some of the things you need in order to calculate it are p-hat, the sample size, and the standard error estimated. Your confidence interval will always be two numbers specifying a range. In the next example right here, which I'll have to do using a different video, I'm going to be going through another example and then also finding the margin of error.